lectures of the Psi year. And some of you might know me. My name is Tibra. I think I interviewed some of you guys on Skype. So that's me, and my office is 274. So I'm teaching this course for the first time, so I will not be able to give you lecture notes. However, on the Psi Wiki, I will be posting the videos of these lectures after they've been uploaded to Persa. And if you want to review some of the stuff that was covered in the lecture notes, you can go and either watch the lecture or you can download the PDF files, which will give you like a screen by screen, screenshots of the lecture. So you basically will have the lecture notes. So the other thing I've done is that I have been very explicit about the books that I've used and the resources I've used for this course. So for example, these are if there's any other resource that I end up using before the course ends, they'll be listed there. So for example, Jones, the representations in physics. I've used his section on tensor methods and Young's tableau. Z wrote a book a few years ago on group theory. Z's been writing this extremely helpful and readable books summarizing what theoretical physicists need. And this is, I think, is the third in that series, and it's called Group Theory in a Nutshell. Unfortunately, I have the only copy out from the library now, but there is a reference copy in the library. And I've ordered 2 extra copies. As soon as they arrive, I'll let you know, and you guys can borrow and, eventually, and share. So I've used if I get to classification of Lie algebras, it'll be probably mainly based on Z. And there's a book by Joglekar on mathematical physics. I've used the volume 2 for essentially today's lecture. A lot of today's lecture is just introducing introductory concepts and, in the context of discrete groups. So, and then Nakahara is applications to geometry. Like you can actually use groups to study geometry. And long ago, I wrote an online book with a student of mine, Matt Robinson. I used the volume 2 of that, just a section to give a heuristic overview of how Lie algebras arise from Lie groups. So that's something that I will not cover in any rigor because it involves introducing a lot of concepts of differential geometry, but I'll sketch the outline, and that's taken from that book. Okay, so the course outline is, can you see it's very small, right? Let me try to make it bigger. Yeah. All right, so this is the course outline. So today I will be we'll be talking about motivations for studying Lie groups and Lie algebra. It's kind of the obligatory waffle that one has to go through at the beginning, but it's actually, I think there's some good stuff there. And then I'll introduce some fundamental concepts and important concepts for group theory, and they'll be mainly done in the context of finite groups. Finite discrete groups, these are not the Lie groups, but it's easier to grasp these concepts in those in that context. And then probably next lecture, we will go to. After the second topic, I forgot to write there. We will talk about what we mean by representation of Lie algebra and a Lie group or a group. In physics, we are not so much interested in the group itself, although we are if it's something new, the structure of the group itself, but its representation, because physical systems furnish representations of groups. So we will have to talk about representation theory. So that'll be somewhere over here. and then how Lie groups and Lie algebras arise from them. And of course, we will mostly be concerned with matrix groups. So after this, we are going to talk about applications of Lie groups to geometry. So I will try to show how the idea of a coset space is related to maximally symmetric spaces in geometry, which is something you need for doing ADS-CFT and stuff like that, for example. After that, we will talk about representation theory of SU2. SU2 is probably the most useful and the most often used group in, theoretical physics and high energy physics. And it crops up everywhere in different guises, and you really have to know, at least if you don't want to care about anything else in Lie groups, you still have to know SU2. So we will do its representation theory, and then we'll do tensor methods and Young tableau for SU2, SU3, and then I'll give you the general rules for SUN. Okay? And after that, the last two topics, I'm not sure if I'll be able to get to them in the time because I'll be going very slowly, and I will do things on the blackboard. I'll take my time. I think just covering something for the sake of covering something is not a good idea. So if time permits, we'll go and do the classification of all the classical Lie algebras. The classical Lie algebras are the Lie algebras that Cartan classified. There are a lot more Lie algebras beyond that, but this is like the first classification, and it's important because it shows the way for other Lie algebras. And then if time permits, so this should also be if time permits, but if time permits, we'll get to the spinor representation of Lorentz group. Okay, so having said these things, I want to, I understand that a lot of you have had courses in Lie algebra and Lie groups, right? Can we see how many of you? Right, so more than half the class, right? So yeah, for you guys, it'll probably be a lot of the things will be, you have seen it before. So the last thing I want to do is to force you to sit through a lecture on something that you've already covered in great depth in some course. So you're still welcome to stay, because I think at some point you will probably come across an idea or notion that you have not seen before, right? And and this is, we try PSI to be an interactive environment, so maybe your discussion will be valuable. So I encourage you to stay, but if you don't want to be in today's class or tomorrow's class, oh, I know this subject too well, I can't be bothered, or whatever, you're welcome to do that. And you can just don't come and go in the middle of the lecture. That kind of ruins the mood. But but if you think, okay, I think I know what's going to happen, that in next lecture, don't show up, I won't take it personally. All right, questions? All right, so let's start then. Okay, I'm going to erase this. Also, this lecture will be about an hour and a half long, and halfway through, we'll take a 5-minute break, because I don't expect anyone to actually be able to hold their concentration for more than 45 minutes. I mean, I know I can't. So, all right, so I think we have already gone through the course outline. So let me skip that. So let's start with motivations. So why do we study groups in physics? What do you guys think? Yeah. They describe symmetries, yes. If you were to answer the question in a single sentence, that's what you would say. They describe symmetries. So you want to be able to describe symmetries of physical system. Right? So for examples, if you don't appreciate how much the symmetries of physical system actually mean, let me give you some examples. So, for example, in 1905, Einstein's theory of special relativity of course, it wasn't called that at that point. It really grew out of his appreciation of the fact that the symmetries of Maxwell's equations were not the symmetries of Newtonian physics. Right? So he basically realized that the symmetries of Maxwell's equations, if we were to take them seriously as the fundamental symmetries of space-time, then the geometry of space-time was radically different. And that notion that the geometry of that Einstein discovered by hitting on the symmetry of Maxwell's equation and taking them to be fundamental was formalized by Einstein's teacher Minkowski into a geometry which is now known as Minkowski geometry. So we know that the fundamental symmetry of flat space-time or geometry of flat space-time came about because Einstein was able to guess, what the symmetries of Maxwell's equation should be. So this is a very partial list. So the standard model of particle physics if you read a book which talks about the history of the standard model of particle physics, you'll see that it was largely the search for the right symmetry group. Like, Salam, Glashow, Weinberg, they proposed a symmetry group to be SU3 cross SU2 cross U1. This is an internal symmetry group. And it's a gauge symmetry, something you'll learn about in QFT. So if you look at any book which talks about the history of it, you'll see that there were other models. For example, there were like SU2 cross SU2, and there was even a G2 model. So different people had different models of unifying the different particle physics. Even now, people several years ago, Garrett Lisi proposed a model based on E8, and but it turned out it didn't work. So this game is still going on. Okay, I'm going to actually I'm going to keep it there because when the board goes up there, you can't really see it because of the glare. So design faults of this room. Okay. There are lots of applications of symmetry, not just in quantum physics, although quantum physics is probably the main motivation, but also in geometry. And okay, let's finish up the quantum physics thing. So in classical field theory, exactly about 100 years ago, like exactly 100 years ago, Emmy Noether showed that symmetries lead to conserved currents or conserved quantity. So, for example, this gives us a deeper insight into why energy is conserved. So the symmetry point of view of why energy is conserved is that, our system, our fundamental laws are time invariant. give me a good example of a system where energy is not conserved. Can you?
Expanding universe.
Good. That's exactly what I was thinking about. So the universe, energy is not conserved, right? Because it's a time-dependent system. And particle is created out of nothing. So this led to a lot of very deep revolutions in physics or breakthroughs in quantum field theory. Which you shall see down the line sometime. And something that I'll just briefly touch upon is one of the motivation is Wigner's theorem. And Wigner showed that the Hilbert space of a quantum system furnish a representation, a unitary and linear representation of the symmetry group of the system. He actually showed that it's either unitary or linear or anti-unitary and antilinear. And in certain cases like time reversal symmetry of quantum field theories, it turns out unitary and linear operators cannot implement that symmetry. We have to actually use anti-unitary and antilinear. And in QFT 1, hopefully you will see that in a tutorial, or at least in at least in standard model. So one of the consequences of this is that the different, there's a there's a link between the mass of a particle and its spin, right? So we know that photon is massless, or helicity states, right? And photon has two helicity states, right? And if it's massive and has spin 1, it has 3 polarizations and things like that. So all of these things were formalized actually comes out of Wigner's theorem. And so there's a classification of particles according to their masses, which comes out of an analysis of the symmetries of space-time known as the Poincare group. So if you want to read more about this, Weinberg's volume 1 has a thorough and somewhat readable discussion on this in the first, I think, 3rd chapter or something, okay? All right, so these are motivations and stuff. So let's dive into group theory then. These blackboards were not a good idea. All right. Okay, any questions so far? Oh, okay. I should ask you, like, what do you think would be your motivation for studying group theory? What do you think is, like, it keeps you up at night? Like, yes, that's why I think group theory is so important. I mean, if you're a condensed matter physicist, you would have very different views on group theory. Like, you'd say, oh, Bloch's theorem, the behavior of wave function in a periodic lattice, that comes out of group theory, right? If you're a quantum information person, you will say, oh no, it's really, what are those groups called? Error correction, those, I I forget the names, but there are these discrete groups which crop up in quantum information a lot, right? So it depends on which part of physics you're in, right? So you will have your own little pet group. So okay, so let's go on to fundamental concepts. So if you're shy and you have a question you don't want to ask in front of the whole class, I mean, I encourage you to ask questions. I am not an expert in this field, so you probably, some of you probably know as much as, or if not more than I do. I will send out a Google a Google form link after the class. So if you have any questions about today's lecture, fill it up before 6 p.m. tonight, and I will try my best to answer that question tomorrow. Okay. And you can also give me some feedback. It won't be anonymous, but All right. So what is a group? So a group is a set G equipped with a binary operation. So this takes you, and so this binary operation is known as the group multiplication, or just multiplication for short, under which as the notation implies, the set remains closed. And satisfies the set must it satisfies the following. So as I already said, closure. So maybe so if A and B are in G, then so is A times B. The multiplication is associative. So it doesn't matter, if you multiply B and C first, and like the order in which, well, right, yeah. So if you multiply these two guys first together, and then multiply A, or if you multiply AB and you multiply C with that product of those two. There are objects in mathematics which are not associative. For example, the octonions. The octonions, yes, yeah. I think the quaternions are associative, right? So there exists a unique element which we call the identity. So this is known as the identity. Now, such that if you multiply any group element A with the identity from the right, you get A back for all elements in G. And fourth, the last one, is inverses for each A in G, there exists a unique inverse, which we say A minus or A inverse, such that if you multiply A by A inverse from the right, you get the identity element. So things follow from this. And I actually am going to make some remarks. The way that the inverse has been defined shows that A inverse is the right inverse, right? Now, you can also show that this is also the left inverse. So let's take a couple of minutes now, if you have pen and paper, and try to work this out. Okay, so let's take 2 minutes and show that so you have to show that this is true. Given
Can we use the fact that E times A is also A?
if it's there.
No, because we define it only as a...
No, that will be the next thing you show. Yeah?
Can we use associative property?
Yeah. So you can use essentially these 4 axioms.
We don't have to require that the identity is the identity go for the.
It actually don't. You don't. I don't think you have to. There may be a way. Yeah, I think so. Yeah. So. All right. So I need a volunteer who has figured this out to come over and give us the solution. Yes, please come over. Please tell me your name again. Sorry? Elliot, like the poet.
You basically just have to use the associative property.
Okay.
Just write that A minus 1A is A minus 1 EA, which is by definition, well, by this property, A minus 1 A minus 1 A, and that.
Okay.
But then you can just switch parentheses.
Yeah.
So you get A minus 1 A minus 1 A, which is nothing else than A minus 1 A squared.
Okay.
So then you just multiply by the inverse of this. And
Ah.
you get that E A minus 1 A 2 minus 1 minus 1. I don't
Okay.
know if it's the same.
Well, there might be a simpler. I think I have a quote unquote simpler way, but logically it's probably the same thing. Right? Yeah. Thank you very much. Yeah. So Somebody else has a different solution, or yeah? Or sorry, he went first. So it's Lucia, right? Lucia, right? Alicia. Sorry, I'm sorry. So you have to tell me your name.
Diego.
Diego. Okay. Okay. So go ahead over there.
So we know from the identity that A is equal to E, right?
Yeah.
And we also know from the that the inverse, the right,
Yeah.
and you use as so
Probably meant A minus 1.
oh yeah. We're here.
Yeah. Yeah.
No, but you're already assuming that
Yeah,
the E.
that's the
You can put the E first, like in.
yeah.
Yeah.
That's right, yeah. Is that
Can we do it? Because you define it.
But that's something that we are assuming that the E is a right.
oh yeah.
Right.
Yeah, you can just call the A on the rightmost A minus 1 minus 1.
Yeah.
Then you get A equals A minus 1 minus 1.
This one.
Yes. A minus 1 inverse.
A minus 1? A inverse? No, I think what he's saying is this, right?
Yes.
Oh, okay,
Yeah?
yes.
Yeah. And then use the fact that, right.
Oh, so yeah.
So I think you
Yeah, I was
that's essentially how I would do it as well. But yeah, I think that's right.
But then you need left identity as well.
You shouldn't. So this is so put the right identity here, right? So let's drop the zeros for multiplication, and then basically and then do what you were trying to do, which is this, right? You can do that, right? And then you can use associativity to kind of say that this is right. And so this, then we can use that fact and call this E. And now this is a right. So, we can just like, right? And that should be equal to E, right?
Yeah.
Yeah. All right, cool. Thank you very much. Yeah. Yeah. No. We are like, it's just like, you should be able to try these things without. All right, cool. So some of the basic ideas of group theory involve these sort of very simple manipulations, which are like set theoretic manipulations. If I were to just jump into Lie groups head on, we wouldn't be able to do this kind of stuff. So if you want more experience with this kind of manipulation and also some logical properties of the multiplication table of set theory, look into Joglekar's book, volume 2. Okay, because he has a lot of these exercises. So that means that the next thing we can show is that the right identity is also the left identity. So if you start by multiplying the identity element from the left, we can write it as like this, so. And then we can use associativity to write these two guys together, and that becomes the right identity. So we see that the left identity is also the right identity. All right, some more remarks before we go for a break. The set G can be finite or infinite. Now, when it's infinite, it can be countably infinite or uncountably. In fact, the Lie groups that we will see will be uncountably infinite. Can someone give me an example of a countably infinite example of a group of a discrete group which is countably infinite?
Set of integers.
Set of integers under what
Addition.
addition? Okay, yeah, very good. The size of the group or the number of elements is known as the order of G. So group multiplication doesn't have to commute. So the definition of a group doesn't tell you that if A and B are two elements of your group, they don't have to be equal to B times A. So if all the elements of G commute, we call the group abelian. Abel was a Norwegian mathematician who made important contribution to group theory and died very young. Who discovered groups? Do you know?
Galois.
Galois. And I think he wrote up his discoveries the night before he died. He had been challenged to a duel, and he was like, "Okay, I'm probably not gonna survive this. So let me just write everything up." It's probably he was awake all night, so he was probably very stressed. So he probably missed. So yeah, that's so yeah. So if there exist, at least two elements, A and B in G, such that AB is not equal to BA, then we call the group non-abelian. Right, so let's do a little example before we break. It's not 1:15 yet. The cyclic group of order 4. So examples. So this is called C4. Now it consists of 4 elements: alpha, alpha squared, alpha cubed, alpha 4, which is the identity element. So by alpha n, I mean alpha multiplied n times. Okay, so this is known as a cyclic group. So so the way I've written the elements of the group, it just it's just obvious what the multiplication table is, right? Like this element is this element times this element, or this element times multiplied with itself 2 times. But I could have written I could have written that this is E is A to the alpha to the 4, and say I label A to be alpha, B to be alpha squared, and C to be alpha cubed. And then I can create what is known as a multiplication table. And it shows that what is, if I take this and multiply it with this, what do I get? I get this. So, and A multiplied E is A. But then if I multiply A with A, what should I get? A with A is A squared, so we get B, right? So, and then C, and then E again. And, there's a pattern emerging. So you might say, why am I doing this? It's clearly perverse to do this when this is so much easier to read off, right? I'm doing this to show that somehow the group multiplication table is what specifies the group. Different mathematical structures might have the same group structure. So for example, this is, say, my example number 1. Let's take another example, which is the integers modded out. So this is the set mod 4. So this is the set of these guys, right? And under addition, mod 4, so we get 0 plus 1 is 1, right? So these are, but if I add now 1 plus 1, that's 2. 1 plus 2 is 3. Then 1 plus 3, because it's it should be 0, right? And 2, 3, 0, 1, 3, 0, 1, 2. And now if I say, okay, I'm going to identify with this E, this with A, this with B, C, then you can check that this multiplication table is exactly the same multiplication table as this thing. So these two groups are actually isomorphic. So this is an example of a group isomorphism. And I think the notation is, I think that's what they use, mathematicians. Not that it matters for me, but Okay. In general, we can, of course, define a cyclic group of order n, where instead of 4, we have n, and it has a lot more elements. Is the cyclic group abelian or non-abelian?
Abelian.
Abelian, right? So yeah, that's obvious. And after, let's take a 5-minute break. Let's meet back here at 20 past, and when we come back, we'll talk about our first non-abelian group. Okay.
It's fine. It's really fine. Do you want to say?
So you get what?
See the menu.
a Google Drive, but that's a
way to do this is following. You go and there should be an edit button. You click on the edit button and it opens up the editing dialog box. And so over here, I'm going to create a new section, lectures. And then I'm going to say, okay, I can, then I will be posting, say, my links to the videos here. Now, underneath this section, you guys should create, like lecture notes by students or lecture notes. And then you can upload your own lecture notes, okay? The wiki is the way it's a little frustrating to use, but I want to emphasize this is for all of you guys to use. If you have resources that you want to share with the rest of the class, please go ahead and use the wiki. It's a okay, so all right, so those of you who were not here, I was showing people how to actually edit the wiki. If you have lecture notes or other resources you want to add, you're welcome to go and add things to the wiki. And if you mess things up, don't worry, let me know, or because I think these things are backed up, so that's not a big deal. All right. Oh. Magic. Okay, so our first example of a non-abelian group. For that, let's talk about one of the simplest but non-trivial permutation group. And actually, it turns out the permutation groups are extremely important, not just in the theory of discrete groups, but also in the representation theory of SUN. It turns out that it's not something that we'll prove. It turns out that the Young tableau, which we will see later in the course, they are actually representations of the permutation groups. So we're looking at the permutation group P3, And what is the permutation of group P3? Suppose you have a collection of 3 objects, A, B, and C. The set of operators, the set of operations, the set of operations on ABC form a group. What are the elements of this group? So these are the elements. Oh, I forgot to mention this part of the course is actually taken from George I's book on Lie groups. I didn't mention it in the list of references. Sorry, I'll add that. I don't like that book very much, although it's physicists use it a lot. But this part is taken from there. So for example, the identity element is do nothing. Is just leave everything as it is. So if ABC is, you leave it like ABC. So the other element, the next element is 1, 2, which is like exchange, objects in position 1 and 2. So if you start with ABC, you end up in BAC. Ends up with BAC. 2 and 3. So exchange objects in position 2 and 3. So if you start with ABC, go to ACB. 1 and 3 is again obvious that it's A, BC will go to CBA. 1, 2, 3, it's kind of a weird notation. There's a matrix notation for this, but you can look that up. But this is more economical for my lecture. So 1, 2, 3 is what was in 1, you take it to 2. What was in 2, you take it to 3. What was in 3, you take it to 1. So this becomes cab. And the last element is 3, 2, 1. And this means that what was in 3, you take it to 2. And what was in 2, you take it to 1. And what was in 1, you take it to 3. And that should give you it should give you BCA. Okay. So it's instructive to ask ourselves, why do these operations actually create a group? So group multiplication is just applying these operations in a consecutive manner. That is just group multiplication. So, but why is it a group?
Because it's permutation, yeah.
Right. So the closed, what does it mean is that after every operation we do, the system, which is the collection of 3 objects, they have a well-defined, configuration. So that's why this forms a group. The fact that after each operation, the system has a a well-defined configuration. And this is an example So this is an example of what we call in physics a transformation group. So a group which transforms a physical system or acts on the state of a physical system to take it to a different state. So the idea is almost laughably simple and obvious for physicists, but it's worth mentioning. Because we're so used to these things, we don't think about these things, right? Okay, so this is an example of a transformation group. As I mentioned, it's a non-abelian group. So it's non-abelian. Okay, Abel was a human being. So for example, if we multiply, if we apply 1, 2 first and then 2, 3, after that, what do we get? So let's see. So we are applying 1, 2 on ABC, so we get BAC, right? And then we apply 2, 3 on BAC afterwards, so we get 2, 3 is this and this, right? BCA. Okay, now if I look over there, what we actually can even see that starting from ABC, we end up with BCA, so we actually get to this element, right? So we can say that this thing is equal to 3, 2, 1, right? And now if I say, okay, what if I apply 2, 3 first and then 1, 2, what is that thing going to be? Well, let's see. 2, 3 acting on ABC should give me ACB, and then 1, 2 acting on ACB should give me CAB, so which is not equal to BCA. And so we conclude that 1, 2 times 2, 3 is 1, 2, 3. So we have shown that this is a non-abelian group. So there is a theorem in group theory. I think it goes by the name of Cayley's theorem. And I'm not going to write down the specific. I don't remember the exact formulation of it, but it goes something like any finite discrete group can be shown to be a subgroup of some permutation group.
Proper permutation.
Sorry?
Proper permutation.
Proper permutations, right? So not improper, like even improper group. Yeah. So that means that the permutation group, as far as the finite groups are concerned, is some kind of universal class, or it provides you with. But I think the proof is more like an existence proof rather than.
You just use the multiplication table, and you can just like show that that's an isomorphism.
Okay.
Just from this, you can see.
Right.
I mean, to E, I assign EABC. To A, I assign ABCA, which is permutation.
Right. Okay.
Basically it. You just have to show that it's a homomorphism.
Right.
So that it multiplies the same way it should.
Okay, cool. Yeah, it's been a while since I read that proof. I actually read it in a A levels textbook in Bangladesh at a wedding. It was my cousin's wedding, and I was just bored, and I was in a room by myself, and there was a A-level math textbook, so I just like opened it up, and oh, there is this amazing theorem. But I haven't read this since then. Anyway. Okay, let's move on to examples of Lie groups.
Sorry, could you just state Cayley's theorem again for me?
Okay, what I think is that so every finite group is a subgroup. You mean proper? Should it be?
I don't know what a proper subgroup is, but the permutations need to be proper because only the identity leaves. I mean, what's the definition? So all the other ones, if you look at the multiplication table, none of the elements are in place except for the one that corresponds to the identity. Then all of the elements are in place, and that means that it's a proper permutation. Proper permutations don't leave any element in the same place.
Okay, I see. Right.
Where we have 1, 2. That
I see. Okay, right. Yeah. Okay. So by proper.
So not the group itself, just a subgroup of the group of proper permutations.
Right. So
same order.
Okay. So right. So we'll get to proper later, but it means that every group has subgroups, and the identity element or the group itself are also subgroups, but they're not proper. They're improper. If there's a subgroup which is actually like a subset which is apart from these two guys, and they form a subgroup, that's a proper subgroup. And I think every finite group is a proper subgroup of a permutation group. And you can look up the proof. All right. So let's give an example of a I'm going way more slowly than I thought I would. It always happens. There's nothing I can do. I'm not going to fight it. We'll just have to speed up in the last lecture. Okay, so this is going to be our example number 4, is the rotation group in 2D. So you guys know all of this probably, but it's still worth. So you take some vector which starts at the origin in 2 dimensions, and so this is the group of rotation of rigid objects in 2D. And then we rotate R by some angle, theta. So R goes from this to some matrix acting on R. The matrix big R, so such that the length of R remains unchanged. Now, if it's a rotation that's continuously connected to the identity, that is, if I take theta to 0, that this we require this matrix to become the identity no rotation, the identity matrix, then this matrix has the form the requirement that this is continuously connected to the identity element excludes reflection. So, so these matrices form a group under under matrix multiplication, as you probably know. And you can verify that this is the form of the matrix multiplication. And because addition of the angle is abelian, it's an abelian group. This condition tells us that, and the fact that it's connected to the identity, that the determinants of these matrices must be 1, and that these matrices are orthogonal, which means the transpose of the matrix gives you the inverse of the matrix. And so this is known as, so this group is known as SO2, and where theta, the parameter, goes from 2 pi to 0. So we're identifying 0 and 2 pi. All of this should be familiar. Now let me give another quickly give you another continuous group that you also know. And hammer in the idea of isomorphism again. So if you now consider all the complex phases, so all the complex phases, so numbers of this form, they form a group under multiplication. So that, as you all know, and if I take a complex number on the Argand plane and multiply it by e to the power I theta, if I represent the complex number by a vector, it rotates the vector, that complex number, by angle theta. So it does exactly what that thing does. And theta, of course, goes from 2 pi to 0. So we can say that all the group of complex phases which form the group U1, that thing is isomorphic to SO2. Later we'll see examples where there are two groups which are not isomorphic but homeomorphic, and the group of rotation is in 3 dimension. SO3 we'll see is homeomorphic to SU2, yeah. And we'll actually explore that geometry in detail. All right, so let's move on to more definitions. I think there's some kind of a, is it like a Russian jet?
What?
Like a Russian jet plane called Su-2 or something? Was it I think it's some sort of a, Yeah?
Yes.
Yeah.
Rock band is also called because of that. Yet.
Sorry, what?
There's a rock band.
Oh, Rock Band, SU2? Oh, U2. Oh, not SU2. Okay, U2. Oh. Yeah, I know U2, yeah. Okay, so you will also meet U2. Not the U2 itself, but you know, like the group U2. Actually, when I first came to PI, PI was a lot more cool place. Don't tell anyone that I said that. I might get fired. The first year I was,
Yeah.
oh, nobody's gonna look at that. It's like some video in an ocean of videos. Nobody's gonna, you know. So, and they actually took us out. Like I actually was late, so I didn't go, but my other colleagues, like all of PI went to a U2 concert paid for by PI.
Wow.
That does not happen anymore. All right, definition, subgroup. So maybe, you know, if U2 breaks up, they can have a subgroup called U1. Okay. So if a subset H of G, so form a group by itself under the same multiplication law, then we say that H is a subgroup of G. Now, if H is not just the identity element or the group itself, if it's not this or the group itself, then we say that H is a proper subgroup. Otherwise, we say H is an improper subgroup. Okay, so what a simple idea. However, it opens up, it leads us to a very important idea, which is called a coset. Now, I'm going to give you the definition of a right coset. You can generalize it to extend it to a left coset as well. So let H be a subgroup. So, so I'm just symbolically writing it as a set, but this set can be continuous. So let H be a proper subgroup of G, and then let G be an element in big G, which is not in H. So it's in the complement of H within G. Then let's for the set where we right multiply G by all the elements in H. Now this set is called the right coset, and it's written like this. So, but of course, the right coset depends on which element we choose. Okay, so this is a very important idea. The right coset is not a group, it's a set, yes?
I understand why you're asking for it not to be in H. For G not to be in H.
So why am I writing that?
Yeah, why that requirement?
Break it down later into
Yeah.
like a so we can represent the G as a sum of cosets.
Yeah.
If it wasn't if G wasn't H, then
Yeah.
Yeah, but that's the
So, so you know, if so, H is itself kind of a trivial coset, right? If G was in H, then it would just be H, right?
Yes.
So that's why we don't choose G to be in H. Otherwise, this set would be just H. If G was not in the complement of H, say G was in H itself,
yes.
then this set would just be H.
Yes, but why would that be bad?
No, that won't be bad. That's not how we are defining it. That's not bad.
I mean,
Let's wait and see where we go. Yeah.
Why would this be H?
Because it's closed under multiplication.
Yeah, it's closed under multiplication, right?
Well, but this doesn't say that you get any element back, right?
Sorry, any?
I mean,
So
the
if
fact that all elements map to an element in H does not say that all elements are mapped to.
oh, I see, right? You're saying whether this is going to actually exhaust. I think it will. You can probably show it very
Yeah,
easily.
you can also get that from Cayley's theorem, sort of.
If it's a discrete group, yeah. But I think you can show that it's actually. I think you can, yeah. So if you have, say, H1 to be, let's take G to be H1, and then H, and so.
Yeah, if you assume that multiplying two different elements will give me the same element, then you lead to like inconsistency.
So you know we would get actually. So we multiply by H inverse, right? We would get the identity, and then you just have to, you know. So I think I can get to. So you know, suppose by multiplying, I want to get to some random element H, right? So I just have to multiply it by H inverse by this thing, right? So I think I would be able to reach any element in the group. Okay? But yeah, good questions. Yeah. So okay, now I won't show it, but you can also.
Excuse me.
Yeah.
When you find that, it's just a definition, but you find that as right coset, typically that would be called the left coset.
Right. Yeah.
Is that?
Well, I mean, yeah. It's just that's the same thing. Yeah. Yeah. So, and yeah, it's just and there's even like a weird coset in string theory called it's an adjoint coset, where you actually identify. Like you form this set. Anyway, we won't go there, but you know that has weird behaviors because that has fixed points. And anyway, so yeah, there are all kinds of cosets you can define, but in mathematics, yeah, right coset is just it'll have the same properties. You know, I just have to choose between left and right. That's why I'm a leftist, so that's why. When I was young, I used to hang out with a lot of Marxist people. So. All right, so you can show that this set G of H is in the complement of H in G. And also it's possible, and for details, look at in Joglekar's book, you can actually decompose the group as a sum of sets which are non-intersecting. For every G G1 and G2 and G3 so on, which is not in H, there is a expansion of this group in terms of the coset. This is known as the coset decomposition. And there's an important notion in geometry called the coset space. And I think I forget the exact symbol that they use. The elements of this coset space are the subgroup and all the other cosets.
Is that the factor group?
It may be called the factor. I don't think it's a group.
Maybe if it's an invariant, if H is an invariant group, maybe then it will be.
If it's a normal subgroup, what you mean? Yeah. But the coset space in geometry, so when G is going to be the, basically these SON groups and H is some subgroup of that, then you can actually show that. So for example, the symmetry group of a two-sphere is, you will see that it's SO3. And within a two-sphere, there is some subgroup SO2. And the SO2 is kind of like a little group. So for example, I think it's some of the points like the North Pole and the South Pole are invariant under rotations of SO2. And then if you form the coset of SO3 over SO2, you can show that that is actually the two-sphere itself. And this, so this is the, so this is basically the two-sphere can be seen as a coset space of two groups. And this geometric fact was very important in the classification of symmetric spaces in geometry. I think it was Cartan, was it somebody, I forget exactly who used these group theoretic methods to explore the geometry of, and if you study string theory and you have to study spheres in God knows how many dimensions, ADS space in God knows how many dimensions, these sort of ideas become very, very useful. Okay.
The coset decomposition, can it be done even if G is non-countable? Yes.
In this case, G is non-countable, right? Yeah. Yeah. And that's why, although that's why I introduced it in this context, but in a different context it is. Okay. All right. So I give an exercise for you to do at home. I'm not gonna check it. So consider, so P2, which is a subgroup of P3, and P2 say consists of the identity element and the 1,2 element. Now work out all the cosets, all the left cosets. With respect to P2. Okay. So
isn't what we defined actually a left coset?
Sorry?
Isn't what we defined actually a left coset, even though we said it was a right one? Because we're multiplying from the left with G.
I think it's called the right coset because we are multiplying G by H on the right. Oh, okay, yeah, sorry.
It doesn't really matter.
No, okay. So I said I was a leftist, but I actually wrote down right? It's okay, I am confused between left and right now. So I have to do a deep... yeah.
According to Wikipedia, it's the left concept.
It's a little...
It doesn't matter.
No, it does. Okay. I gotta be true to my roots, man. Okay, in the last 5 minutes, let me go through the 5 pages of lecture notes that I have. No, I'm just kidding. Okay, so normal or invariant subgroups. So if for all elements in a group, we have that when we multiply the subgroup H by all these elements, it basically commute that with the subgroup, then we say then H is a normal or invariant subgroup. So if G, for example, is an abelian group, any subgroup is automatically normal or invariant. So this leads us to a very important definition. The definition is that of a simple group if E and G are the only normal subgroups of G, then we say that G is simple. A related notion is the center after having lived in the United States for 6 years, but having spent many years in Canada and the UK, I'm no longer sure how to spell these words. And having come from Bangladesh, wherein the light switch goes the other way than here in North America, and in England it goes like in Bangladesh, I still don't know how to turn a light, whether I mean, of course you can see whether the light is on or not, right? But I have a bulb in my house where it only lights up when it's warm, So I don't know whether it's actually on or off. All right. The center is a subset Z of G is called the center if for all elements in Z and G we have sorry. Okay, so at some point, this definitions I think should come in handy. So in the next class, we will start on representation theory, and we will also at least get into Lie groups and Lie algebras. There's a tutorial tomorrow at 3:45, your first tutorial, and that tutorial will be on the Lorentz group and how the electromagnetic fields form a rank 2 tensor under the Lorentz group. You know, it might be familiar, but I think it's really worth doing. Okay? So I'll see you guys tomorrow. Yeah?
Just that last definition.
Yeah.
Like as it's written, a group could have multiple centers, right? But shouldn't it just be a unique center? Like right now.
It's a set of all elements that commute with all elements in the group. So.
But that's not.
Okay, yeah, that's not what we wrote.
Yeah.
Like, oh, I see. So you're saying.
Like right now, I could make the set containing just the identity would always.
Usually, it's fine just with all.
So okay, so yeah, sorry, I wasn't being rigorous. So it's all the elements. Thank you. Okay.
Thanks.
No, thanks for keeping me.
Can I ask a stupid question?
There is no such thing, but yes.
I mean, I remember that when I studied this before, we defined like the simple group and whatever, but I don't know exactly where we use it. And you said this is an important.
Yeah, it's used when we do the classification of Lie algebras. I think.
For algebras, but not for groups, and not for finite groups.
Not for finite groups, yeah.
Okay, so for now it's not important.
Yeah,
Later we'll need
yeah. Yeah, you had a question?
So the Coset decomposition is a decomposition in terms of the set.
Right.
Not group.
Yeah.
In the Coset space, you also that quotient, yeah?
Yeah.
Is a set.
Yeah. Great. Yeah. All right. Great, guys. Thank you. Yeah.